Today I wanted to take some results from the core project 3, which had to do really with the interaction of superplasticizers of the polycarboxylate type with the aluminate phases. And what I would like to do is to emphasize some of the implications of the main findings of that research and put them a bit in the big picture of thinking about how admixtures work. The work was done by Claire Giraudot, Claire Lenain at the time. She's now in Schlumberger. The PhD was carried out at ESPCI under the direction of Jean-Baptiste Despinoz, but also co-advised by André Nona from the University of Burgundy. Myself, I was one of the industrial advisors, but also initiator of the project. And Dr. Martin Mosquet was also involved, and Irene Schauber was very important in that she supplied the polymers that were used in the study. So it's quite a fun working team, and I try to present some of the outcomes and little extra stuff around it. First of all, some of you might have seen me use this slide before, but I like to state that in the concrete area, one tends to think about chemical admixtures a little bit like dark arts. So I use this slide. In Harry Potter, you suspect Professor Snape to be a dark wizard, and he's got a course also of potion making, which is basically chemistry at Hogwarts. And there's superplasticizers, viscosity modifiers, accelerators, air entrainers, shrinkage reducers, corrosion inhibitors, and grinding aids. And all of these allow you to make really advanced concrete, to make things that one couldn't make before, to pump concrete very high, at very large distances, to have it self-compacting, high strength, etc. So, what can one do with advanced concrete technology? One example, taking from Switzerland, and I added this slide as the vice president said he was a geologist. You know about maybe the Gotthard Tunnel, which has been built 157 kilometers of excavated distance. The amount of rock that was removed from under the tunnel would have allowed Switzerland to build 5 Cheops pyramids. You imagine for the Swiss tourism the boom that would have been. Anyway, somewhere we're missing a bit of innovation. And the speed of construction was really possible because of advanced concrete technology and solutions through admixtures. Unfortunately, some people have creative ideas also, not necessarily in the good way. You heard recently about the votation in Switzerland, wanting to kind of stop too much immigration. Well, there's, if you've read the press this morning, the Swiss government actually has a plan to build an anti-immigration wall around Switzerland using, no, don't laugh, using the rock from the Gotthard Tunnel. Somebody calculated that it can be 1 meter wide and 7 meters high, and the ETH and EPFL, you probably will get the email as I just got on my computer, are planning to use advanced concrete technology to do this without foreign work. So that's what I was telling you about the dark side of admixtures. You get asked to do all kinds of things and then you wonder if it's reasonable or not. Anyway, I'm just kidding. An anti-migration wall would not make it possible for foreigners to deposit their money in our banks. So, more seriously, let's talk about what one can do with chemical admixtures and advanced solutions. So, these are substances that work when added in small amounts, and the reason why they are so effective is that they act at interfaces. So think about concrete with solid, liquid, vapor phases at different stages of its life. You have solid-liquid interfaces that control processes of agglomeration, adsorption, dispersion, that control dissolution, nucleation, and growth, crystallization pressure, or creep. Liquid-vapor interfaces controlling capillary pressure, surface tension, air entrainment, solid-vapor interfaces for dry dispersion or hydration pressure, for example. And you can fill in the diagram, avoiding, of course, the vapor-vapor. interface, and not forgetting solid-liquid interfaces, which are important for corrosion. So now, as we're talking about the chemical admixture area, if you look at a product portfolio of any of the big companies present, you'll find corrosion inhibitors, you'll find shrinkage reducers, air entrainers, you'll find grinding aids and cement improvers, and you'll find accelerators, retarders, or superplasticizers. So all of these are very effective in small amounts because they act at interfaces, and they have therefore a common set of physical-chemical questions which govern their behavior. And the thing I want to really talk about today is superplasticizers. So I think the first thing to emphasize is that good superplasticizers do not always behave the way they should. That is something that is found in various areas of life, including football. With this image here, you see Zidane lifting the World Cup, and here you see him a couple years later. And essentially, the challenge is to try and avoid misbehavior. So to try and design molecular structures of superplasticizers that avoid them not performing as they should, depending on the opponent, so to say. So what's the simple picture that essentially we can use as a framework for thinking is that if you start with a flocculated system of particles that are sticking together in the concrete, the fine particles, you add a superplasticizer which absorbs on the surface, disperses, and you get independently moving particles which can flow, and you get something which is more fluid, you can put less water, get higher strength, etc. And the concept is that if in one way or another you lose part of the admixture, the degree of surface coverage is reduced, and this leads to some degree of flocculation in the system, which means that the fluidity of your material will be impaired. And the question that the Nanocem project addressed is there such a waste product? What is it? What can we learn about it to try and prevent it from forming? There were a certain number of clues before, in particular in the thesis of Valérie Fernon, who examined oligomers of polynaphthalene sulfonate and found that they tended to intercalate in AFM. As she moved to polynaphthalene sulfonate, she was no more able to observe the structures as they tended to be more amorphous, and the project essentially led to the speculation of some kind of structure of the sort existing, and this is also an idea that I brought forward further with a colleague in EPFL during my PhD. So what kind of structures are we thinking about, or were we thinking about? Well, they are layered double hydroxides, which have divalent and trivalent cations in sheets, and in between you have anions, which are charge balancing, and organics, negatively charged organics in principle can also be there. So this was imagined as a kind of a trap for these admixtures, and we will discuss how relevant this model really is. Anyway, looking outside of the cement literature, the layered double hydroxide is a fruitful area of research. For example, for drug delivery, people are looking at these systems, and there's all kinds of compounds that you can create. People have tested various types of molecules, shown that the basal system varies as a function of the molecule that you put in, and also that the formation of these phases is not restricted to the formation with very small organic compounds, but that you can include large molecules, alginates, and even DNA. Now, there's two important things to emphasize here. First is, as you increase the size, you tend to lose a little bit the nice X-ray signals. You get a lower angle peak appearing, which corresponds to the larger layer spacing. And very large molecules as DNA, you can produce these structures if you do it in an in-pot reaction, meaning that the precipitation of your phase takes place in the presence of the organic additive. If you add it afterwards, it won't happen when the molecule is very large. So there's been various efforts to try and understand this process. One of these has taken place at TU Munich. There's been a lot of work there that was not in the core project, but I mentioned their initial main approach, although they have taken other approaches since. Oops. Okay, so the approach there was to use C3A and a polycarboxylate polymer at 75 degrees for 48 hours and then analyze the product. And what they have found is that you find nice layered structures that you can characterize very nicely by transmission electron microscopy. They identified that these phases can form and that although thermodynamically without the polymer you would not expect the laminar phase to be stable, the polymer does stabilize them. Now what I would like to move to is the work that came out in this publication and was really coming out of this core project from Nanocem. And I try to emphasize the specific contributions of this project. And here I wanted to put that other slide before. That was just summarizing what Professor Flatt reported, and we also found that under normal conditions, the laminar phase will convert to a cubic phase, but in presence of the polymer it is stabilized, and this conversion does not take place. Okay, so the approach taken in this core project was one of precipitation. That was the main approach. So solution of sodium aluminate with polymer mixed with a calcium hydroxide solution leading to the precipitation of composite C4AHX polymer phase, but also the possibility of precipitating this phase without the polymer and adding it subsequently. And by keeping everything at a low temperature, we avoid the conversion to the cubic phase. So we're testing whether these layers, once formed, make it possible for the polymer kind of to creep in and move the phases apart. So that was the real reason why working at 5 degrees here. So the next important contribution of this project is to look at this through the eyes of NMR. And the reason for this is that, as I mentioned, the earlier work by Valérie Ferrand showed that you lost crystallinity very rapidly. It was difficult to use, therefore, XRD diffraction to get something valuable. And NMR, in principle, is an adequate tool to look also at amorphous materials. So what you see on this graph is for 3 different polymers that there is a clear shift in the aluminum NMR spectrum, which is indicating that you have an intimate interaction between the polymer and the aluminate phase. What's more interesting is that you have exactly the same shift if you do this in delayed addition. So whether the polymer is present during the precipitation or added afterwards, you get the same result. That is an important result here. The next important one, the values here actually, this is an early analysis of experiments which were not fully adequate as we were just measuring the harmonic of the main peak. But nevertheless, what we find, again, for immediate and delayed addition is that the spectrum is giving a basal spacing harmonic peak at equivalent distances, whether in immediate or delayed addition, and that the large side chains, as also reported by Professor Planck, did not lead to intercalation. So let's move forward. We also can determine that there is a reminder of the in-plane reflections from this phase, therefore we really can trust this kind of LDH model with intercalated polymers. And with the kind of layer spacing that we get, these values actually will be revised on one of the later slides. we move towards the idea of a coiled conformation of the side chains in this interlayer. Now this has been a debated subject, and the approach again here, which has been unique in the core project, has been to use a special NMR sequence referred to as trapdoor, transfer of population by double resonance, and the main idea is to test whether protons from the polymer are close spatially to those of the mineral surface. And as I'm not myself the NMR specialist here, I will use a cartoon to try and explain the idea. And the concept is that it's as if you want to measure the difference in speed between a tortoise and a rabbit, but you do it in a little bit complex way. So you say go, and they start to run, but you're not measuring anything. And then you get them to go in the other direction, inverse polarization, you go back, and after a certain time, when they're back past the start line, or at that corresponding time, you start to measure. It's only then that you measure. And the question is, if you do something on the way back to perturb the behavior of one of them, for introduce a little carrot. And then on the way back, the rabbit is going to be slowed down, and your final measurement is going to show a difference, which is that somehow the rabbit has been perturbed by something, and this something in the experiment of the trapdoor is the irradiation of the aluminum ions. So in this sense, you're probing whether specific protons in the polymer are close or not to the surface of the aluminum. And here would be one of our spectrums without aluminum irradiation. You do the aluminum irradiation and you get this very modified spectra. You can do the spectra difference and identify the protons mainly from the side chains. There's not enough mobility from the backbone to see something. And what we can conclude from this is that the side chains in these structures must be coiled. So that is, I think, one of the important results that came out of this study. I have to say that the state of dryness of the sample will obviously affect a bit your result. And it is important when we try to understand structures in relation to what a behavior may be in a paste to try and work at high humidity and not dry the hell out of the systems. So, another interesting result, which actually made me very happy, was that the student was still puzzled by these relatively narrow spacings that we were getting in the XRD diffraction. And so she said, oh, it might be the drying, so we got the samples equilibrated at 100% humidity, a couple of tricks to do the X-ray diffraction there, but also went to a place where she could do these measurements at small angles. And what happened is that we just realized, what I alluded to before, that the peaks that we've been looking at were just the harmonics of the main basal spacing. And that a normal XRD measurement will not be able to detect those very low angle peaks. And the nice thing also was that, this is where I was particularly happy, but whatever, we had in a separate study by atomic force microscopy concluded that the adsorbed polymers had to have coiled side chains and that there would be a scaling law approach that we could use to infer the characteristic dimensions of the polymer and a characteristic dimension if two layers with adsorbed polymers would come into contact before you would have massive steric repulsion. So what she did then was to take the calculated layer based on the parameters from this separate publication and plot it versus what she measured at interlayer spacing. And the slope is exactly 2, and the intercept is what you would get without polymer. So it's kind of the result almost too good to be true. The typical thing that one would want to have repeated, but it was done at the last in the last stretch of the PhD. So anyway, I think it's quite an interesting result, but it raises a very important question. Why would a phase which is separated by so many nanometers of what normally is a good steric hindrance dispersant have a cohesion? I think this question has not been addressed enough. In my opinion, at the moment when in these precipitation reactions we separate the material through the filtration process and the accumulation of platelets on the filter, there's a certain degree of organization. Then we take a TEM measurement of this, and in a coupled zones we have some number of platelets that are roughly parallel. And this spacing is governed by the presence of the polymer. So this is consistent. But what it really means for cement paste is that I don't expect that one really forms in cement paste these layers. One might form platelets that are dispersed, and I believe that these platelets can act then as seeds or for etrangite nucleation once sulfate concentrations change. So this brings me to this notion of how stable these phases are in presence of sulfates, and that's another area where I think this core project has made very interesting contributions, and these have come from measuring the ion concentrations in solution during the formation of these phases. So what you have here is, first of all, you form these platelets without the polymer, hydrocalamine, and then at some point in time you add the polymer, and what do you see? The concentration in aluminum increases, reaches a maximum, and then goes down to a lower level as the initial. The next plot shows something similar for calcium, starting a bit higher, also going through a maximum and decreasing exactly at the same time. If you look at the organic compound in the solution, it is constant over time. You've added it in the solution and it's remaining there, and then eventually it goes down also. So I find this a fantastically beautiful plot, because it's indicating that you have a process of dissolution of the phase. You reach a certain critical supersaturation where you have nucleation, and once you've passed here this nucleation point, you get the growth, and this growth consumes the aluminum, calcium, and polymer to form this new phase. Is this new phase a set of dispersed platelets or platelets that are parallel? I think they're dispersed. We had actually results that suggested that, but we have never properly written them up. Yeah, so that's something we probably have to do. And yeah, so you have this process of dissolution and critical supersaturation, nucleation, and growth. So the intercalation is not layers in between which the polymer comes and cranks them open and little by little moves. It's something going through solution. That is an important learning, and the fact that if you look at the incorporation of the polymer in the AFM phase, you have this very non-trivial consumption of the polymer also suggests that we're facing a non-trivial behavior which is not just one of absorption and plateau. So the teachings here, again, are that these polymers have a strong effect on the reactivity of the aluminate phases, on the nucleation and probably growth of these phases as AFM or monosulfate and also etrangite. So I think that's another of the broader reaching results of this PhD, which I think has not yet been fully realized. Then a couple other nice things. You have here a plot of amount of charges associated from the polymer to the solid or from sulfates, which are added at time 0 to the system. And what you observe is quick adsorption initially, a latent period, and then a decrease of the amount of polymer associated to the solid and an increase of the sulfate. So you don't suddenly go to monosulfate. No, there is a period in these experiments, under these conditions, with these concentrations, where you have to wait a certain time for something to happen. And the kind of picture is that you have something of the sort, you add some sulfates, you go to a monosulfate phase, and some polymers remain in solution. What I think was also very nice was to show that this latent time depending on the nature of the polymer. And that depending on the spacing of the side chains, so the ionicity of the backbone, or the length of the side chains, and the complete length of the polymer, you have different times until this destabilization takes place. So that raises the question, we don't know exactly what this time would be in a real system. It's very certain, it's certainly dependent on the sulfate concentration. There's lots of sulfated cement. In properly sulfated systems, it's maybe not that relevant. But there's an important information that there is a process that might last a certain time, which is not negligible with respect to the 1 or 2 hours of open time that you would like to have. The question is, do we suddenly release more polymer after a certain time and the material becomes more fluid, for example? Or do we have one phase which gets lost by creating a lot of these platelets, but it's stable, so it's not creating a perturbation? So I think these are questions that are still worth thinking about. And this morning I was scratching my head about thinking how to present this, and it dawned on me that, well, actually it's something I had in mind for a fair amount of time, that the notion of competitive adsorption with other ions as sulfates, which is something that is known to perturb the action of superplasticizers, should in principle be roughly at stake also here. And in a separate work I derived first principle relation for an adsorption equilibrium constant, so this has its limitations, but it did allow to qualify polymers that were not or resistant to competition with sulfates from ones that are susceptible to sulfates. And the high value of this constant would mean that you would not be bothered by the presence of sulfates, and the low value that you would. So I took the values of the polymers here. It's the first time I did it, so there's no cheating. It's derived from another set of data. And you get this fantastic relation. So I'm not going to claim that it has to be linear or whatever form, but there is a very reasonable consistency in this separately determined constant that relates to the adsorption capacity of a polymer and this latent time for hydration. So this obviously needs to be checked with other polymers, and bringing out the idea like that, I find it pretty nice to see things coming together. So I'm going to move towards brushing up. I think this is important in the sense that you have the different molecular parameters of the polymer in the equation, and it's telling you that single polymer structure analysis of problems of dispersion in concrete are almost certainly bound to fail. It's the combination of the different parameters that eventually governs the properties. And you can think about it, if you like to think about the side chain length, that alone is not sufficient. That also will depend on the application. You don't always have the same requirements. And I like to use the example of height in sport. It's useful in basketball, but obviously not very necessary in football to be well performing. And to expand this as I approach the conclusion, it's important also to realize that commercial products often contain different components, so it's more like building a football team than having an individual player. and that even good football teams, which work well in the most cases, sometimes have errors, like Spain losing to Switzerland when they won the World Cup just afterwards. So today I kind of talked to you about some unexpected behaviors, unacceptable behaviors, and try to relate what one can understand about it. It all roughly still fits into this picture that I proposed some number of years ago, where you have polymer added, divided between a consumed part and an excess part remaining in solution, a part adsorbed, which is relevant to dispersion, and this relating to the initial surface, adsorption extent and amount, conformation dictating the rheology, but that part of the material might be lost, and that over time, and probably very quickly in the first stages of hydration, we have formation of additional surfaces which are there and consume part of the excess and basically therefore perturb the overall or the time evolution of the superplasticizer's efficiency. So with this, I think my time is up. I just would like to emphasize that this is an exciting subject. I think Nanocem has made a nice contribution to this field. And there's a number of ongoing research projects in different areas. I mentioned one in TU Munich with a recent publication trying to suggest how the chemical composition of a cement might or not dictate the probability of formation or perturbation of rheology because of intercalation. The PhD thesis of Florent Dallas, recently defended in the University of Burgundy, in the link of how surface changes caused or facilitated by the polymer modify also in turn the rheology. We're working on similar areas, struggling with the notion of how to best determine the specific surface of these materials. And the equation I mentioned before was derived for understanding the competition between accelerators and superplasticizers, and that has also recently been published. So it's a subject of ongoing actuality, a fun one, and I hope there'll be there is another ongoing project and other fun projects in Nanocem. So with that, I'd like to thank you for your attention.